How can a ball get from one side of a wall to the other? Well, it could go over the wall or around the wall. It could also go asterisk through asterisk the wall, but that would leave a big hole, right? But what if I told you the ball could pass straight through the wall, leaving it completely undamaged? In our everyday world, that sounds impossible. But in the strange world of quantum physics, it's not only possible, it happens all the time. This phenomenon is called quantum tunneling. For tiny particles, like electrons, scientists have seen this happen for ages. But tunneling for big objects, like you see in Harry Potter, has never been observed in reality. Though, theoretically, it's not impossible. The 2025 Nobel Prize in Physics was actually awarded to 3 scientists who managed to observe tunneling in something much bigger than a single electron. Today, we're diving into what quantum tunneling is and why this Nobel Prize is such a huge deal. I'm Zuman, and you're watching Big Yin Pacey. So, imagine an object in a room. How do we pinpoint its exact location? We need 3 pieces of information: its distance from one wall, its distance from another, and its distance from the floor. With these x, y, and z coordinates, we can perfectly map out where any visible object is. But for the building blocks of those objects' subatomic particles, like electrons, protons, or neutrons, it's a different story. It's absolutely impossible to know their exact location. Now, you might be thinking, wait a minute, if all big objects are just collections of these tiny particles, why can we pinpoint the location of a chair, but not the electrons inside it? That's because the rules are completely different for the big and the small. We can treat a chair as a simple particle, but an electron, it's not just a particle, it also behaves like a wave. Think of it like this. A particle is at one specific point. A wave, however, is spread out across a region of space. A subatomic particle, weirdly enough, is both. It can exist in multiple places at the same time. The famous Double-Slit experiment proves this beautifully. If you fire a stream of electrons at a wall with 2 tiny slits, you don't just get 2 lines on the detector screen behind it. Instead, you get a complex interference pattern. Exactly what you'd expect if waves were passing through and interacting with each other. This wave-like nature is fundamental. It even explains the very shape of atoms, as described by the Schrödinger wave equation. So, what does this have to do with tunneling? Let's look at a simple hydrogen atom. We can't say the electron is orbiting the nucleus like a tiny planet. Instead, the wave equation gives us a probability cloud. This cloud shows us where the electron is asterisk, most likely asterisk to be found. The denser the cloud, the higher the probability. The electron isn't in one spot. It's smeared out across this entire cloud, existing everywhere, in it at once. Now, let's bring back our wall. Imagine an electron on one side of a wall, or what physicists call an energy barrier. Because of its wave-like nature, the electron's probability cloud isn't just on one side. A tiny part of that wave, a tiny piece of that probability, actually extends asterisk through asterisk, the barrier, and exists on the other side. This means there's a small, but non-zero chance that, if you go looking for the electron, you'll suddenly find it on the other side of the wall without it ever having broken through. It just appeared there. That is quantum tunneling. It's a real, proven phenomenon. In fact, you're alive because of it. The sun shines because of quantum tunneling. In the sun's core, the temperature isn't quite high enough for hydrogen atoms to smash together and fuse because their positive charges push each other away. This repulsion creates a massive energy barrier. But thanks to tunneling, some of those hydrogen nuclei just pop through that barrier, allowing nuclear fusion to happen and power our entire solar system. Modern technology like the scanning tunneling microscope also uses this effect to see individual atoms. Until recently, we'd only seen tunneling with tiny individual particles. But this is where the 2025 Nobel Prize winners made their breakthrough. They observed it in a much larger system. To understand how, we need to talk about superconductivity. When you cool certain materials down to extremely low temperatures, all their electrical resistance vanishes. Electrons flow through them perfectly with zero energy loss. In 1957, the BCS theory explained how this works. It proposed that in a superconductor, electrons don't move alone. They form pairs, called Cooper pairs. These aren't physically stuck together. One electron slightly warps the atomic structure around it, and that distortion guides another electron, making them act as a pair. What's amazing is that all the millions of Cooper pairs in a superconductor act in perfect unison like a single giant quantum entity. This brings us to Brian Josephson in 1962. As a 22-year-old student, he predicted that if you put a very thin insulating barrier between two superconductors, the Cooper pairs could quantum tunnel across that gap. A current could flow with zero voltage, which should be impossible. 4 years. This was just a theory, but in the mid-1980s, the three scientists who would win the 2025 Nobel Prize finally proved it. They built a device called a Josephson junction and confirmed the effect. They saw a current flowing across the insulator with no voltage, a macroscopic sign of quantum tunneling. By controlling this effect, they showed that quantum phenomena weren't just weird things happening to single particles. They could be harnessed on a larger scale. This was a monumental step towards building powerful new technologies, especially quantum computers. You might ask, why didn't Josephson get the 2025 prize? He actually won his Nobel back in 1973 for the theory itself. This new prize honors the experimentalists who brought his vision to life. The quantum world is bizarre and defies our common sense, but it's the foundation for the future of technology. Just as the quantum world has its puzzles, so does our everyday world. For instance, if the Earth is a sphere, why don't people on the bottom fall off? And if it's spinning so fast, why don't we all get flung into space? For the answers to these classic questions, check out this video right here. And if you enjoyed learning with us today, be sure to subscribe and become part of the Big and Pacey family. Thanks for watching.